is going to deal with transforming quadratic functions and specifically using vertex form. To begin with, we need to understand what the parent function looks like. This is going to be y, or f of x, equals x squared, and it's going to graph like a parabola. Now, we're going to bring in some transformations that should look familiar to us from moving absolute value functions recently, namely the variables a, h, and k. A is going to be our amplitude, and if a is a value whose absolute value is greater than 1, meaning it could be positive or negative, but if it's, when we take the absolute value, if it's larger than 1, then it's going to look as though it's a vertical stretch. If it's some fraction or decimal between the values of 0 and 1, positive or negative, it's going to be a vertical shrink. The negative tells us that it's going to reflect vertically, which means it's going to be oriented downward. So that's the a value sitting out front. The h and the k are going to have horizontal and vertical shifts, and this is a useful form for us because when written as it is above, the h and the k are going to combine together to give us our vertex. A parabola is going to have that arcing shape, and depending on its orientation, it's either going to be pointing upward, which means it's going to have a low point, or downward, which means it's going to have a high point. And that high or low point is known as the vertex. H comma k is vertex form. So our vertex form is going to look as it's written on the screen now, and it's not, it doesn't need to be g of x, but if we consider f of x to be our parent function, the next letter alphabetically is g. If we're going to transform it, g follows f, so we need to know what f looks like. So here is our first example for today. What if we take our parent function, and instead of just having f of x, what if we have x minus 2 inside parentheses and minus 4? If you can see how that's written on the left-hand side, the f of x could be any parent function. In future chapters, we'll be dealing with other types of functions. If we apply it specifically to the function that we have, then we can look over to the right and see that it's x minus 2 all squared minus 4. If we understand vertex form, then we should say that our vertex is going to be at 2 comma negative 4. And currently, I'm not looking at an amplitude. We could call that a value of 1. So that's going to look just like the parent function in terms of stretch or shrink or reflection, but we're going to shift to the right and down. If we take a look at our parent function graphed here on Desmos and take a look at the first example, we should just take our parabola and go 2 units to the right and 4 units down. And I have a couple of other points graphed just so that you can see there's an axis of symmetry right here at x equals 2. That's the value, the x value of the vertex. It has a low point of negative 4. So if you're going to talk about the range, we go from negative 4 to positive infinity. And that's how that first one graphs. Now, second example. It looks exactly like the first, except I've thrown a 2 in front. Now the 2 is an amplitude, but if you notice as it's written, I'm only multiplying the 2 times the parentheses. I'm not impacting the minus 4. So my vertex is still going to be at 2 negative 4. Now my amplitude is 2. When we were performing transformations earlier, if we said, take that function and now vertically stretch it, we would have to multiply the 2 times the whole function, and so we would multiply it times the negative 4 also, but that's not the case here. So when we come back to our graph, if we look at our second example, it's the same vertex 2 negative 4, but it's been vertically stretched from that point, and so to get from 2 negative 4 up to 3 negative 3, for example, we would rise 1, run 1. Now to get up to the point on the purple, we'd have to rise 2 and run 1. Why? Because there's been a vertical stretch by a factor of 2. You can see if we went over 2 units and came to for the first example. Now we're going to come over to 4 and be up at positive 4. Instead of rising 4, we're rising 8. Why? Because we've doubled our vertical stretch. Let's take a look at another example. What if we have an amplitude of -1/2, an h value of 3, and a k value of 2? Bringing that over into our specific quadratics, we still now would have a vertex of 3, 2. Everything is setting up nicely, but our vertex now is, our amplitude is -1/2. So I have a pretty good feeling that we're going to shift 3 units to the right and 2 units up. But the amplitude has 2 things happening. There's a negative and there's a 1/2. What does the -2 do and what does the 1/2 do? When we take a look, I have 2 things graphed here. The orange is specifically what we're looking for, but the red dotted is just the parent function shifted 3 units to the right, 2 units up, and then reflected downward. When we throw the 1/2 in, you can see where we normally would have 2, 1. We're now at 2, 1.5. We've shrunk by a factor of 1/2. So it looks wider than the parent function. A fourth example. An amplitude of +5. Inside the parentheses, we have x plus 1, and outside we have -8. When we bring that over into the specific example with the quadratic, there's a problem, and I don't know if you notice it right away, but remember the parent function, or the way we would want to talk about the transformations would be x minus h, and we have a x plus 1. I'd like to consider that to be x minus -1, which would suggest that we are -1, -8 for our vertex. So in other words, when we see x plus 1, it's a shift 1 unit to the left, whereas if it's x minus 1, it's 1 unit to the right. What we're wondering is, what value do we need to plug in for x in order to make this expression within the parentheses equal to 0? And that's why -1 is our answer. The a is obviously 5, but I want to note that it's +5. We're going to be oriented upward still, but we're going to have a vertical stretch. So looking at this example, you can see that we've gone from the origin 1 unit left and 8 units down. So our vertex is now at -1, -8. And again, the red dotted graph here, parabola, is just simply the shift. And then when we apply the stretch to it from that vertex, -1, -8, we're stretching up by a factor of 5. So rather than going up 1 and over 1 to get to 0, -7, we've got to go up 5 and over 1 to get to 0, -3. Or the symmetry would tell us that we could go up and over to the left to get to -2, -3. Finally, one more example is, can we find the formula, the equation for a parabola in vertex form, if the vertex is at 3, 4, and if it passes through the point 6, 0? What is that going to look like? So I have typed in here vertex form for us. We also know the vertex, so I feel pretty comfortable that we can plug in a 3 and a 4. The problem is, we don't know the amplitude. We have to be able to solve for A. So what to do? Well, I've color-coded it, so hopefully you can see we have a little bit more information that we pass through the point 6, 0. So we should be able to plug those values in, 0 for y and 6 for x. And now it's a matter of trying to solve. If we subtract the 4 to the other side, it becomes negative. Inside the parentheses, 6 minus 3 is 3, and 3 squared is 9. So we have negative 4 equals 9a. And if we work a little bit further, we get that our amplitude is negative 4/9, which goes on to suggest that our equation should have an amplitude of negative 4/9 and the vertex of 3, 4. Let's take a quick look at that. And we should find, we want to be slow today, sorry about that. We're passing through 3, 4. We're passing through 6, 0. And if there's any symmetry here at all, to go from the axis of symmetry 3 units to the right over to 6, 0, we should also be able to go 3 units to the left and get to the origin.